Hey everyone, welcome back to the Incredible India podcast series. I'm Taylor,
And I'm Sam.
and today we are going on a bit of a mission. We are going to completely dismantle one of the most, famous and deeply entrenched timelines in the entire history of science.
We really are. It's a huge paradigm shift in this deep dive today.
It is. So I want you listening to think about something you use, like every single day, probably without even giving it a second thought. Think about the GPS on your phone.
Right, yeah.
You pull it out, you type in a destination, and a satellite hovering thousands of miles above the Earth just, pinpoints your exact location and guides you turn by turn.
Which is honestly a modern miracle.
Exactly.
Mhm.
But that technology relies entirely on highly advanced calculus. And if you open basically any history of science textbook in any classroom around the globe, they'll insist that the mathematical foundations of that calculus were invented by Isaac Newton.
Right, in England, right around what, 1666?
Yeah, exactly, 1666. But today we're looking at sources that prove the real foundational framework was actually laid down more than 200 years earlier.
2 whole centuries.
Yeah, by a man named Madhava in a small town in 14th century Kerala, India.
And the sources we're analyzing today, they present this profound shift. When historians talk about the development of math, Newton and Gottfried Leibniz are virtually always presented as the undisputed architects of calculus.
It's just treated as gospel, right?
Totally. It's a timeline that feels completely set in stone. But the texts we're exploring reveal a totally different reality. Madhava of Sangamagrama, he was born around 1340 CE. He was doing the exact same sophisticated mathematical heavy lifting that we credit to European scholars who, wouldn't even be born for another couple of centuries.
We really need to unpack this carefully because to understand just how shocking Madhava's achievement is, we first have to look at what preceded him.
Right, the context.
Yeah, how he totally transformed the math of his era. So we're focusing on South India, but we actually need to look a little bit north of Kerala first, up to Karnataka, about 2 centuries before Madhava even enters the picture.
Yeah, taking that step back is crucial because Madhava didn't invent these concepts out of thin air.
Right.
He was the culmination of this incredibly rich, ongoing Indian mathematical tradition. So specifically, we have to look at a brilliant mathematician named Bhaskar II.
Okay, Bhaskar II.
Yeah, he was from Bijapur in Karnataka, and in the year 1150 CE, he wrote this landmark text called the Siddhanta Shiromani. And the fascinating thing about him is that he was already using foundational calculus concepts long before Europe even had a word for them.
Wow, like what kind of concepts?
Well, he was actively working with ideas like instantaneous velocity and describing mathematical functions that approach limits.
But if I'm reading the sources correctly, he wasn't doing this just for the sake of pure math, right? He was developing these tools for a very specific practical reason,
Yeah.
mostly for astronomy.
Astronomy was the primary driver, absolutely. Because tracking the movement of planets, it means tracking curves and continuous change.
Right, you can't just use straight lines.
Exactly. You cannot do that accurately with basic algebra. So Bhaskara applied what we would now recognize as differential calculus techniques, but he used them specifically to solve particular isolated problems in planetary motion.
Okay, so hiding specific applications.
Yeah. Brilliantly using calculus ideas, but entirely within the context of specific astronomical puzzles.
Okay, so I was thinking about this evolution, and here's an analogy that might help you listening. Sort of picture the difference between these two massive thinkers.
Oh, let's hear it.
So think of Bhaskara II as this incredibly talented visionary engineer. He encounters a massive roaring river, and he figures out the exact, highly specific physics and math required to build one very specific, brilliant custom bridge across that particular river.
I like that. So it works perfectly for that one crossing.
Right. But Madhava, coming along 200 years later, he wasn't just an engineer. He was the theoretical physicist who looked at that one bridge, analyzed it, and wrote down the universal laws of gravity and tension that allow absolutely anyone to build any bridge anywhere in the world.
That framing captures the transition perfectly.
Because he took Bhaskara's highly specific applications and formalized them into a complete universal system.
You really did. Bhaskara demonstrated that the concepts worked in action for specific problems, but Madhava took the decisive, world-changing step of formalizing the underlying mathematical machinery.
He built the actual framework.
Right, the theoretical framework that allows those exact same concepts to be applied universally to any trigonometric function. It was this massive leap from a specific, localized application to a generalized system.
So these two traditions, flowing from Karnataka down to Kerala, they're really just sequential chapters in the same extraordinary story.
Exactly. Together, they represent the single most significant contribution to the development of calculus made anywhere in the world prior to Newton.
Okay, so we know Madhava created this universal system. But let's actually get into the mechanics of what that looked like in practice, because this brings us to what the sources highlight as his most groundbreaking, reality-bending work.
Oh, the infinite series.
Yes, the infinite series.
To really appreciate the infinite series, we kind of have to demystify what it actually is and why it completely broke the boundaries of traditional math.
Yeah, please do.
So in ancient math, across the globe, scholars mostly dealt with finite procedures. A finite mathematical procedure basically gives you an exact answer using a fixed, countable number of steps.
Like basic geometry.
Right. If you want to find the area of a standard rectangle, you just multiply the length by the width. 2 steps. You arrive at an exact, perfect, undeniable answer.
Hang on, though. I'm not a mathematician, but if you're dealing with things that aren't perfectly straight rectangles, things with curves, you can't just multiply 2 numbers. You get irrational quantities, right?
Precisely. The physical world is just full of quantities that simply cannot be calculated exactly, using a finite number of steps.
Like pi.
Yes, think about the value of pi, which you need for any circular calculation. Or the sine of an angle.
Yeah.
Or an arctangent. These are irrational.
Meaning they just keep going.
Right. You can approach them with increasing precision, but you can never reach them exactly by just doing a fixed number of standard algebraic calculations. They represent a fundamental wall that ancient math just kept running into.
So if you can't reach the exact number in a few steps, how do you solve it? And this is where I really need you to break it down for me, because the sources say Madhava solved this using an infinite series, which involves adding infinitely many terms.
Right.
But if you add an infinite amount of numbers together, wouldn't the answer just be, well, infinity? How does adding things forever equal an exact finite number?
That is the exact paradox that held math back for centuries. It's so counterintuitive. So to understand how Madhava solved it, imagine you're standing in a room facing a wall that is exactly 10 feet away.
Okay, I'm facing the wall.
Your goal is to reach the wall, but the rule is you can only move by stepping exactly half the remaining distance.
Okay, so my first step covers 5 feet.
Yep, your first step covers 5 feet. Then your next step is half of the remaining distance, so 2.5 feet.
Right.
Then your next step is 1.25 feet, and so on.
I see the problem. I'll just be taking microscopic shuffles forever. I'll literally never physically touch the wall in a finite number of steps.
But where are you ultimately heading?
The wall?
The wall. The wall is your limit. An infinite series works the exact same way. It is a sum of infinitely many terms that get progressively smaller.
Oh, I see.
You're adding and subtracting more and more tiny fractions, and the series theoretically never terminates. But with each new tiny fraction you add or subtract, the answer converges closer and closer to the exact value.
Wow.
It was the decisive step from the finite, rigid procedures of ancient algebra to the limit passage to infinity. Madhava basically figured out how to mathematically map those infinite microscopic shuffles.
To make this even more intuitive for you listening, imagine you're manually focusing a camera lens on a really beautiful landscape.
Oh, that's a good way to look at it.
Yeah, at first the image is blurry. You twist the lens a little bit, making a fractional adjustment that's like adding the first number in the series. The picture gets a little clearer, but it's still fuzzy.
Right.
So you make a slightly smaller adjustment.
Yeah.
Then an even smaller adjustment. With every tiny fractional turn, adding or subtracting a progressively smaller and smaller number, the image of the mathematical truth gets sharper and sharper until it converges perfectly.
Exactly.
You never technically stop tweaking the dial, but the image becomes functionally flawless.
The camera lens is a brilliant visualization, and the real-world application of this mechanism is just staggering. I mean, Madhava discovered the infinite series expansions for sine, cosine, tangent, and arctangent.
Which is huge.
Huge. But the most celebrated one in the sources is his series for pi. It states that pi divided by 4 equals 1 minus 1/3 plus 1/5 minus 1/7 plus 1/9, and so on indefinitely.
Let me just translate that so no one gets left behind. You're taking the number 1, and then you're looking at the odd numbers 3, 5, 7, 9. You divide 1 by those odd numbers, and you just alternate subtracting and adding them forever.
That is the exact formula. It's an alternating series of the reciprocals of successive odd numbers.
And using that exact infinite series formula, Madhava calculated the value of pi correctly to 11 decimal places. In the 14th century,
Yes.
3.14159263359. That's wild.
To accomplish that without a calculator requires just an astonishing level of mental discipline and theoretical clarity.
It is actually mind-bending when you stop and think about the sheer contrast here. Going back to our earlier example with the GPS, to make modern GPS systems function accurately across the globe, you need pi calculated to about 15 decimal places.
And he hit 11.
He hit 11 decimal places centuries before the first mechanical computers were even a concept. And let's set the scene here. He wasn't doing this on a massive chalkboard in a climate-controlled university in London.
No, definitely not.
He was scratching this highly advanced mathematical analysis onto vulnerable palm leaves using an iron stylus in the middle of a tropical, deeply humid climate.
The physical reality of his work brings up a deeply tragic point about historical preservation, actually.
Yeah.
Those palm leaves, which were dried, treated fronds of the Palmyra palm, were highly vulnerable to the environment. I mean, between the humidity, the local insects, and the heavy, relentless monsoons of the Kerala coast, physical texts had a very limited lifespan.
It just wouldn't last.
Right. Almost all of Madhava's original manuscripts, his actual handwritten calculations, have been completely lost to time.
Wait, if that's true, if his original work literally rotted away in the jungle humidity, how on earth do we even know about him today?
It's a great question.
Like, how do we have his exact formula and his 11 decimal places of pi if the palm leaves disintegrated?
We only know about him because of the institution he built, the Kerala School of Astronomy and Mathematics. It survived and thrived for over 200 years after his death, primarily through a rigorous system called the Guru-Shishya tradition.
The teacher-student oral tradition.
Exactly. And it is far more than just casual storytelling. It's the direct, incredibly rigorous transmission of exact knowledge from a teacher to a student across multiple generations.
Oh, wow.
Because the physical manuscripts were so fragile, the mathematical knowledge was preserved in the minds and the subsequent writings of his intellectual descendants. They essentially acted as human hard drives.
So the students were rewriting and referencing his work before the original leaves could rot.
Precisely. Students like Parameshvara and later a brilliant scholar named Nilakantha Somayaji in the 15th and 16th centuries.
Nilakantha.
Right, Nilakantha wrote a massive foundational text called the Tantra Sangraha, and in it, he doesn't just present the math, he meticulously cites and quotes Madhava's original discoveries.
So he gave him credit.
Yes. He explicitly attributes these infinite series formulas back to his predecessor. The students preserved his mathematical genius by constantly referencing his priority in their own later surviving works.
But despite all of that meticulous citation by his students, despite them doing everything right to preserve his name, a massive historical tragedy of misplaced credit occurred.
Yeah, it really did.
Because 200 to 300 years later, European mathematicians suddenly discovered these exact same series, and the narrative completely shifted.
The timeline of this European rediscovery raises really complex questions about how history is recorded, validated, and taught globally.
Absolutely.
Take the arctangent series we were just breaking down. A Scottish mathematician named James Gregory published it in 1671. Gottfried Leibniz published it independently in 1676.
Right.
As a result, if you walk into any university calculus course in the world today, from New York to Tokyo, that formula is definitively taught as the Gregory-Leibniz series.
Even though Madhava knew it, formalized it, and taught it 3 centuries earlier.
The exact same dynamic applies to the series for sine and cosine. They're taught globally as the Newton series or the Taylor series.
It's just so frustrating.
Well, there are historians today who are actively pushing to rename these formulas to reflect their true documented origins. They advocate for calling them the Madhava-Newton series, the Madhava-Leibniz series, or the Madhava-Gregory series.
Which makes sense.
But those compound names are still largely unknown outside of highly niche mathematical history circles.
And I have to push back on this. On behalf of anyone listening who's as frustrated by this as I am, we have Cambridge University professors like George Gheverghese Joseph explicitly stating in the sources that Madhava's priority is, and I quote, beyond doubt.
Yes.
It is an established, peer-reviewed historical fact.
Yeah.
So why are global textbooks so agonizingly slow to adopt names like the Madhava-Gregory series?
It's a valid question.
Is it just standard academic inertia, where it's simply too expensive for publishers to rewrite and reprint the books? Or is there a deeper reluctance to decenter European history? because from the outside, it feels like the global education system is actively resisting the idea that the foundational math of the modern world came from a village in India.
The resistance is likely a complex friction point involving both factors, honestly. Academic inertia is undeniably powerful. I mean, once a term like Taylor series has been embedded in millions of textbooks, academic papers, and standardized tests for over a century, changing it requires a monumental, highly coordinated global effort.
Yeah, that's true.
But observers also point to the deeply entrenched narrative of the European Enlightenment. For centuries, the prevailing historical story has been that modern science was exclusively a product of Western Europe.
Right, the classic Western-centric view.
Yeah. Acknowledging that a 14th century Kerala mathematician laid the groundwork for calculus significantly disrupts that neat narrative. But regardless of the reasons for the delay in textbooks, the underlying priority question is settled among experts. Madhava was there first, by a very long margin.
Okay, which leads us perfectly into what has to be the ultimate historical whodunit. Because this debate over credit brings up an even more explosive, controversial question.
The transmission theory.
Exactly. Did Newton, Leibniz, and Gregory really just happen to discover these exact same formulas independently centuries later? Or did Madhava's math secretly leak out of India and travel to Europe?
This is where the story shifts from a simple timeline correction into a genuine historical mystery, often referred to as the Jesuit transmission theory.
Tell me about this, because this is fascinating.
To understand how this could even be possible, we have to look closely at the geography and the geopolitical climate of the time. Madhava was born in Sangamagrama, which is present-day Irinjalakuda, in the Thrissur district of Kerala. And very close to this area was the ancient, legendary port of Muziris.
Which is now linked to the Padmanabh archaeological site, right?
Correct. And in the 15th and 16th centuries, this coastal region was not some isolated backwater. It was one of the most commercially active cosmopolitan trading hubs in the entire world.
A major global hub.
Right. Picture the scene. The air smells of cardamom and black pepper. You have ancient spice trade routes, Arab dhows, and a massive influx of international wealth. By the 16th century, European navigators and armadas began arriving in force, and traveling alongside those merchants and soldiers came the Jesuit missionaries.
Okay, so you have European math nerds living right next door to Indian math geniuses. But when most people hear the word missionaries, they picture priests standing on corners holding Bibles. How does highly complex calculus physically get from a Jesuit in Kerala to James Gregory in Scotland in the 1600s?
To answer that, we have to rethink who the Jesuits were during this era. They were extraordinarily well-educated men, functioning as the scientists, astronomers, and scholars of their religious order. Many of the Jesuits who arrived in India had incredibly strong mathematical backgrounds. When they established themselves in Kerala, they didn't just preach to the locals, they fully immersed themselves in the academic culture.
They were studying.
They learned the complex regional languages, they actively sought out and studied ancient Sanskrit manuscripts, and they were directly interacting with the very scholars who were studying and copying the Kerala school's mathematical texts.
And they had a direct postal route back to the universities of Europe.
Yes, they were in active, constant written communication with the leading mathematical and scientific centers of Europe. They were essentially operating as academic intelligence gatherers, situated right in the middle of the exact region where the Kerala school's mathematical manuscripts were actively circulating.
This is just so thrilling to think about. You have the exact formulas existing in Kerala. You have highly educated European mathematicians living down the street from the Indian scholars teaching those formulas. And you have an established network of letters going straight back to Europe.
It's the perfect setup.
In any detective story, the suspects had the motive, the means, and the opportunity.
The circumstantial evidence supporting transmission is incredibly compelling. The mathematical similarities between the late results produced by the Kerala school and the early calculus of Europe are striking.
Too similar to be a coincidence.
Many think so. The maritime communication networks absolutely existed. The Jesuits possessed the technical capability to translate and understand the advanced math, and they had the clear motivation to send any useful navigational or scientific knowledge back to their superiors in Europe.
Despite all of that perfect setup, we don't have the ultimate proof.
That remains the massive catch. Historians still lack the definitive smoking gun. To this day, there is no specific letter that has been found, no crumbling manuscript in a European archive with a Jesuit priest's handwriting saying, "I have translated an incredible infinite series for pi from an Indian scholar named Madhava. Please share this with Mr. Newton."
But just imagine it for a second. With the sheer volume of documents the Jesuits produced, it is entirely possible that such a letter exists.
Absolutely possible.
It might currently be sitting, completely unread, misfiled, and unremarked in some dusty archive box in Rome or Lisbon, just waiting for a graduate researcher to open the right folder and permanently, undeniably rewrite the entire history of science.
The possibility is undeniably tantalizing for historians. And until that specific document is found, the transmission theory will remain a fiercely debated hypothesis.
Of course.
But it is vital to remember that regardless of whether the knowledge was secretly transmitted or genuinely rediscovered independently by Europe, Madhava's individual genius remains undisputed. He grasped the formal concept of a limit, the very conceptual foundation of calculus in 14th century Kerala.
So as we wrap up this exploration, I want to leave you listening with a lingering thought. Think back to those fragile palm leaves disintegrating in the monsoon rains and the crushing humidity of the Kerala coast.
Yeah, it's wild to think about.
We only know about Madhava's brilliance because his students were incredibly diligent about quoting him before the leaves rotted. It makes you wonder how much other ancient paradigm-shifting knowledge has been completely, permanently lost to the climate. Or, even more provocatively, how much of it was simply assimilated, repackaged, and renamed by later empires.
Right.
What other Newtons of the ancient world are hidden in plain sight, just waiting for forgotten students' notes to be translated and finally read?
If you decide to travel to Kerala, we have a recommendation. 5 Senses Tours organizes tours across India, which are immersive cultural experiences. You can email contact@fivesensestours.com. Note 5 is written as a numeral in contact at fivesensescourse.com or WhatsApp 2+ 919-845-677-446.
The next time you open your phone and that little blue GPS dot finds you on the map, take a second. Realize that the math calculating your exact position isn't just a triumph of 17th century Europe. You're being guided from space by the brilliance of a 14th century mind, looking at the infinite from a small village in incredible India. Thanks for taking this deep dive with us, everyone. We'll catch you on the next one.